Hello everyone. In this video we are going to talk about solution of 1D elliptic and parabolic PDEs. If you're not sure about the definition of elliptic and or parabolic or other types of PDEs, please refer to my channel, and there is a playlist called Partial Differential Equations, and in that one you will be able to see how we define different types of PDEs. So we are going to focus on 1D PDEs. Okay, so all you will see is your dependent variable is a function of time and at most one special variable. Here you might call it x. So the general form of the equation or equations that it can solve is like this: that the function c times first derivative of u with respect to t equals x to the power negative m times partial derivative with respect to x of x to the m, the function f, plus the function s. These functions c, f, and s in general can be functions of the position x, the time t, the dependent variable u, and the first derivative of u with respect to position. Now, m here, the parameter m that you can see is called the symmetric constant, right? If your problem has slab symmetry, which is basically defined over a symmetric rectangular area, you need to insert number 0. If it's defined over a cylindrical area, the number is going to be 1, and if it's over a spherical symmetric area, it is going to be 2. That's one thing. 2, it is going to solve it for the range of time t between t0 to tf, where the tf, you don't have really much of a limit on it, but of course you don't want to ask, because it is a numerical solution, you don't want to ask MATLAB to solve it for a very long time, because it is going to take a lot of time of your computer. But mathematically there is no limitation in MATLAB here on tf, but in the range x between a to b over the distance domain, it has to be finite. You cannot solve the PDE over an infinite physical domain. The functions f and s. F is called the flux term and s is called a source term, right? For example, if you look at the heat equation, right, if the example we are going to solve is going to be heat conduction over a simple 1D bar with constant initial and boundary conditions, right? So here, basically what you have, if I want to draw it, is going to be a simple bar like this, a physical bar, and then at one end and at the other end. So if we here say this is the x-axis, at this x equal a, you try to keep t1 to be constant, and at x equal b, which is the other end, you also try to keep it another constant in this problem that we are going to solve. And then overall you give it an initial temperature of T, x and 0 equals to some constant like T0. So now the goal is at any specific location x, you want to find what is the temperature at that location at any time point. So this is the physics of the problem, and the flux term and the source term. Source term is if you have any basically source of heat in the domain that is basically giving you heat at any time point, a value of heat flux, and we don't have such a thing. So in our case there will be no s is going to be 0. And the flux here is what we have for heat conduction. If you remember, the heat conduction Q dot, which is the amount of heat energy per time, is negative K, which is the conductivity of the material, times A, which is the cross-section of the material, times dt over dx, which is the gradient of temperature with respect to location. Correct? So that is the heat flux, or if you want the density of it, you can divide both sides by A, right? So that's what you really have here for the flux term. That's what we have, the heat flux. Okay, so since we are going to also solve it over a place that has no cylindrical or spherical symmetry, and it's just like a line, which is like a 1D version of a rectangular area, you can have the symmetry to be 0 here, M. Now the heat equation is a parabolic PDE, and again, if you want further detailed explanation of what PDE is parabolic, which one is hyperbolic, which one is elliptic, please watch the videos I have under the playlist partial differential equations. But in here, for this case, the equation, we can say that have a time derivative, they are parabolic. If they don't, they are elliptic. So this one only, this command only solves parabolic and elliptic, not hyperbolic PDEs. And there are some other conditions, like for example, the flux term F does depend on partial derivative of U. U here is the same as temperature T with respect to X, so does depend on dt over dx. And the other thing is, when you here multiply the function C by partial of U with respect to T, it is just a simple multiplication, okay? So you cannot have these terms basically and any other term than multiplied by partial of U with respect to T, okay? And also with respect to time in general, okay? The only thing you can have is a product that exists between them. So if you want to use the command PDEpe, the MATLAB solver for the first order or first 1D parabolic and elliptic PDEs, you need to define several things. First, you need to define the entire PDE in such format. So you have to figure out your S function, your C function, your F function, and the value of M. If we want to do it in this case here, so here I'm going to write my equation, partial of U with respect to T equal to second derivative of U with respect to X. Again, U here is the temperature. You can write it in the format of the general thing that is expected. And so there is no C function that is multiplied to partial of U with respect to T other than 1. So your C function is simply 1. As I said, in this case, there is no X term multiplied outside of the partial of U with respect to X, or the second derivative of U with respect to X. There is no power of X, so M is 0. There is no source, so S is 0. And the function that you are taking partial of with respect to X is simply partial of U with respect to X. Because once you take partial of this U with respect to X again, you get second derivative of U with respect to X. So F is derivative of U with respect to X, S and M are 0, C is 1, okay? That's how you write your function called PDEfun. That's basically after M, which is the symmetry constant, and in this case it's 0, everything else, including S, F, and C, they will all be defined in PDEfun, right? So you see this PDEpe gets several input arguments: the symmetry parameter M, the functions F, C, and S, then the initial condition, and then the boundary condition. You need to provide a mesh for X, you need to provide the time points for T, and then options for controlling the error, right? So what we have so far found that m is 0, and then these functions c, f, and s are given like that. So when we go to MATLAB and we want to code it, that's what you do. You say function c, f, and s is equal to whatever name that you want to give it of x, t, u, and du over dx, where c is 1, f is du over dx, and s is what? 0. So this one here is exactly going to be your what? Your PDE function. Here I call it heat PDE, right? By the way, this code is directly coming from MATLAB help, so I have not written any part of it myself. So this is the function that defines S, F, and C, and you clearly see here I have passed m of 0 to my PDEpe. So now it is time to go and talk about what? Initial conditions and the initial condition and the boundary condition here. So the initial condition is very easy. In this case, it is just a fixed number, right? So defining the function IC_fun should be very easy. All I do here is I call it hit initial condition. Again, you can call it whatever you want, and I define the constant value of u0. In general, it is a function of x, right? Because your function u in general is a function of x and t, but when t is 0 initially, then it is pure function of x. So here this u0 could be any function of x, but I just decided to go with a constant number. So of, let's say, 0.5 degrees Celsius or Fahrenheit or whatever unit that you want. For boundary condition, it's a little bit more involved. You again have to follow a specific format, and the format of it is like this. A function p plus a function q times the same function f that we had earlier should be equal to 0. Okay? And here your goal is to figure out the functions p and q, both for the left and the right boundary of this kind of beam here. So if I write my boundary conditions, one of them was u of 0 and t was 0, the other one is u of L and t was 1. So how can I write u of 0 and t equals 0 in this format? Well, I write it as u of 0 and t plus 0 times f equals 0, because there is no f function. And remember, f was what? In our case, it was partial derivative of u with respect to x. Since there is no condition of partial of u with respect to x in here, therefore, this coefficient multiplied by f, which is your q function, that's 0, right? And your p function is just u of 0 and t, or u of the left boundary. So you can say p for the left is u of the left boundary, which you here set it at 0. And q for the left boundary is also what? 0. The same thing for the right side. U of L and t equal 1. You can write it as u of L and t minus 1 plus 0 times f equals 0. Again, the q function is going to be 0, but the p function is going to be u of the right-hand side minus 1, right? So this is clearly your q, and this guy is clearly your what? Your p function, right? And again, similar thing here. This is your p, and this coefficient multiplied by f is q, okay? So you clearly see your p and q of the left and right. And this is what we describe in our MATLAB code here. So if I go to my MATLAB code, I have this function called heat boundary condition, and here I have to provide you with x of left, x of right, and then I pass to it x of left, u of left, x of right, u of right, and t in general. If it's a function of all of them, in this case it's not, it's just a bunch of numbers. And then p of left is simply u of left. and Q of left is 0, P of right is U of right minus 1, and Q of right is 0. And here, as I said, U is the same as temperature, right? So all of these four guys are exactly what you can see here, right? And clearly in this case, my boundary conditions do not depend on the x of right or x of left. They don't depend on the location, and they do not depend on time. They only depend on the constant numbers of u left and u right that I will be providing later in my solver. Okay, so this is the boundary condition, this is the initial condition, this is the main PDE described. And before I move forward, I want to talk about one thing. You might say, well, when the temperature is constant, right? So the temperature at, let's say, the left side or right side is constant, then this function q should always be 0 because there is no f, so the coefficient of f has to be 0. Is there any case that this q is non-zero? Is there any case that this function f shows up on the boundary condition? And the answer is yes. In this case, remember, your f was what? This whole f was partial of u with respect to x, or partial of temperature with respect to x. Is there anywhere on the boundary condition that this guy shows up? And the answer is yes. Remember, I told you that the heat flux is negative Ka dt over dx. Now, if you go on one of these boundaries and instead of setting that boundary at a constant temperature, you do what? You say, well, at this boundary, instead of a constant temperature, I am going to seal it. So if I have heat insulation here, and I don't allow the heat to go in and go out, so this is heat insulation. That means what? That means Q dot has to be 0, the heat flux. And when Q dot is 0 means what? dt over dx is 0 because A and K are non-zero. And that is the same as your function f. So you can write it as f equals 0. This is going to be your boundary condition now. And if you want to write it as what we had, which was P plus Q times F equals 0, you have to write this as what? 0 plus 1 times F equals 0. So if you compare these two, you'll see that in this case, your P is going to be 0 and your Q function is going to be 1. So yes, there are scenarios where Q can be non-zero, and that's where you have what? Heat insulation. But if you have constant temperature, then Q is going to be 0 and P is going to be non-zero. Good. So now if we go to our syntax of the function, you clearly see we have defined the first 4 input arguments. So now I just need to tell it to generate so many elements in the x direction and how many time points to use. And if I want to tell it about where to stop, right, about the relative or absolute error, which in this case I'm not going to do it, I can add it to the options. But as I said, the goal is to break this whole domain into a bunch of subdomains, a bunch of elements, right? So that's what we call mesh. So you determine how many of these elements you need, and then in how many time points you do it. And then once you figure this t of x of t, then you can plot it, right? You can have this temperature, and you can see something like a contour plot, or you can use the image command to see it as something in 2D. So you can have one of your axes be x, the other one be t, and then at each point you plot t of x and t here, and you can show it as I'm about to show you right now. So now you go here. I used 1 meter for the length of the bar, and I generated 20 elements in the x direction. And for time points, I'm using 40 points unequally spaced. Why? Because typically, as the solution moves forward, it converges fast toward the steady state solution. And as it gets closer and closer to the steady state, then the speed of change of t does go down. So you really do not need close time points together to capture all of those fast variations in temperature. So in the first, let's say 1 second, I used 20 time points, but in the next 9 seconds, I also used 29 points. So I use a total of 40 points, but the first 20 of them happen in the first second. The other 20 points of them happen in the next 9 seconds, right? So after 1 second, my time points are a little bit further away from each other because now, almost after like a second or so, I have come very close to the steady state solution. So that's my time points. This is my number of elements or mesh. And now I call my function and it gives me the solution u, which is the same as temperature, as I said. And as I said here, I'm using the image command, image sc command, to do like a better visualization. I also added the color map of hot because this is a heat problem and a color bar. So if we run it, this is the result. As you can see, the x-axis is the location, the y-axis is the time, and the values show temperature. The value on the right hand side is 1. The value on the left hand side is always 0 at any time point. And anywhere else other than these two boundary points in the beginning, when t was 0 in the beginning, pay attention that your the ticks of the time axis are upside down. So the smallest t is on the top, not at the bottom. And that's because you're using the image command. So the values here at t of 0 for all points except for the boundary conditions are 0.5, the average value. And when the conduction starts, the heat starts to penetrate from the hotter areas to the colder areas, right? So you see this area that was black, of course, it's going to stay black because you fix the boundary conditions on the right side. These guys are not going to change, but if you see now, these several nodes that you had here, and they were all red, right? Now they all turn to yellow, correct? And at the same time, these nodes that were all 0.5 are now what? They are going to lose a little bit of their heat. Why? Because they are trying to pass the heat to somewhere that has a temperature of 0. So the direction of gradient of temperature, dt over dx, is from right to left. The temperature should flow from right side to left side. Okay, this way. And let me insert an arrow. So this direction here is clearly q dot, or dt over dx. Right, this is the heat flux direction. So the thing is, when the heat gets to this side, because it's not insulated, the heat gets wasted away from the left side, let's say by convection or any other methods of dissipation of heat. So you're losing heat on the left side. And for that reason, since you're losing heat and the heat is coming, but that's not enough to compensate for the loss of temperature, over time you see these elements that are close to the cold connection on the left, they start getting colder, and so their values drop from 0.5 to smaller than 0.5. On the other hand, these nodes on the right hand side, which are connected to a source of heat or source of temperature, the temperature of which does not go down at all and it's always kept at a constant temperature, the temperature of these guys go up. They were 0.5, so now they are yellow. They are about 0.7, 0.8. And so it keeps going, these variations. You see when you go down, you see some changes in the values. But these changes continue until what? Until some time. After some time, if you look at each one of these columns in the time direction, you don't see much of a change anymore. So now it is kind of what we call a steady state situation. So if I want to break it down for you, I can say, for example, maybe this much of it or something like that, right? This area here is going to be like transient heat or transient response. This is in the beginning, right? And then the portion to the bottom of that, all of this region is going to be like steady state. Correct? And I can use double arrows, of course, as well. So let me use double arrows here. Here. So this whole thing is, as I said, steady state. And this small portion here is basically the transient response. Okay, so hopefully it's clear what we are doing here. And if it's a lot of time for steady state, then you can bring it down. You don't need to simulate it for 10 seconds. If in less than a second you get to close to steady state, maybe you just simulate it for 2 seconds. But the first second maybe you use 50 points. The next 1 second you use just 10 points, right? And use as many elements as you want. Maybe you don't need those many elements. Maybe you do. Maybe you need to make more elements. Of course, the more elements, the more time points, the more it takes to solve. Maybe you want to change your boundary conditions to some bigger values, like make the temperature on the right side to be 10 and make the initial value to be, let's say, 2 or 3 or something. Let's take it off that symmetric case. Right, so feel free to play with it and look at the effect. So now you can see the heat waves clearly going from right to left. But again, after you see about 0.4, 0.5, 0.6 seconds, the columns start to kind of be uniform. Right, that means you reach almost a steady state solution, and that's because the K value that you chose here was big. Right, so if you want, you can go ahead and change your K value. Remember that your du over dt, which is q dot, is a constant times dt over dx. And that constant here is basically defined by your 1 over c. So this c is inversely proportional to k, the conductivity. If you make this C bigger, means conductivity is smaller, right? So if you want, you can make this C a little bit bigger to slow down the process of heat conduction, right? So now it should not be as fast. Now, let me see here, and maybe go back to that 4. You have to run the script, not the function. And now you clearly see, even after 2 seconds, I'm not completely down to uniform columns. So the process is taking more time, and you can see the effect of it a lot better. So hopefully solving this heat equation using the command PDEpe and creating these functions for boundary condition, initial condition, and the PD itself was useful to you. Feel free to change all of these, right? If you want to make this a function of L, you can do so, right? You can say, for example, L is 1. You can say this is like sine of x, correct? The only thing is this should not have conflict with your boundary condition, because your boundary condition are now 0 and 10. This one is not going to get 0 and 10 for you. In x of 0, it does 0, but in x of 1, it's definitely not going to get you 10. Unless you say 10 times sine of x and then divided by sine of 1. So now at x of 1, this generates 10. So the initial and the boundary conditions are now not going to have any problem with each other. So you always need to make sure these two corner points, let me show them to you and then we finish the video. These two corner points here, if I can insert an ellipse, this point here, right, and then this point here. These 2 points, you have to make very careful attention to them, that these points, the boundary and the initial conditions, do not contradict each other. So hopefully it was useful to you, and I will see you in my next video. Thank you.